What did you say we were going on to?
We are going over section 3.5 today.
Okay.
So of course it won't be on the test that's due tomorrow, but now the next this next test is the shortest, I believe, of all the tests. There's only going to be 3 sections on it. Hold on.
You're talking about test 4?
Yeah, test 4 is a shorter one. If you go into the schedule, you'll see that. And it's because really chapter 3 is kind of a longer section, or I'm sorry, chapter 3.5, section 3.5, I should say. Section 3.5 might take us more than today to lecture on. We'll just see as we go along.
All right.
It's just a longer section, and it's not like you can make it 2 sections. It's just kind of the topic takes a while.
Yeah, it is long in the book. I'm sitting here trying to get to the beginning of it.
Yeah.
From the back. Okay. There we go.
It's kind of one of my favorite sections to lecture on. But okay, so yeah, let's start on section 3.5. So 3.5 is on the rational functions and their graphs. So let me get this kind of situated how I like it. Rational functions. So let's start there. Rational functions. A rational function is just any function written as a fraction. It's kind of the easiest way to think of it. Your book says it's a function with 2 functions, one on the top and bottom. So they say p of x over q of x, and you'll see that notation throughout the book. There's nothing wrong with that, and we've seen rational functions already. It's not like our first time seeing them. I mean, if I gave you a function like this, f of x equals 2x minus 1 over x plus 3, right? We've seen this already with the domain section in 2.6. And really remember, the domain comes from q of x for this example. So let's just start there. If I asked you for the domain, that's going to be the first kind of question anyway, and it's a review. Remember the domain, that denominator could not be 0, right? So if x plus 3 can't be 0, x cannot be negative 3, but this means we go from negative infinity to negative 3, and then union negative 3 to infinity. That was old stuff, right? Let's look at kind of a more basic one, and then we'll kind of go about, well, in this section, we're going to talk about what happens at that negative 3. That's the first thing, actually, we're going to talk about. So let's look at another example. Let's look at, let's say, g of x up here. And we'll make it kind of basic. 2 over x minus, let's do x minus 3. So if I ask you the same question, I ask you, well, what's the domain? Look, if I ask you what the domain is, you never worry about the numerator, okay? Does not matter. It could be a giraffe in the numerator. We're not worried about it. We're going to act like it's not there. It's like the elephant in the room or the giraffe in the room. But we're not going to worry about it. We're just going to look at this denominator. And we're going to say x minus 3 can't be 0. Therefore, x cannot be 3. And then we're going to write it as an interval. Negative infinity to 3, union 3 to infinity. You know, that was just the way we wrote it. Well, now section 3.5 starts with what is happening at 3, right? We can't plug 3 back in. So if you try to do that, right, if I tried to plug 3 in, I get 2 over 3 minus 3. I get 2 over 0. And remember, anything divided by 0 technically is undefined. So we can't graph it because it's not a number. It's undefined, right? Okay, so I'm going to rewrite this. Hold on just a second. We've got g of x here is our function. 2 over x minus 3. And we know that the only restriction, these are called restrictions on the domain, right? The only restriction we have here is that x cannot be 3. But we're curious, what is happening at 3? We know we can't plug it in, gives us back undefined. So the way I kind of jokingly explain how to figure out what's happening at 3, it's like if you were set up on a blind date, okay? You're set up on a blind date. I'm going to make this table. x, okay, g of x. You set up on a blind date, and you're wanting to figure out about this guy or gal, number 3, okay? You can't just call number 3 because that's weird. If you call him or her, they might think you're weird, and it's just never going to get off. It's not going to get off to a good start, right? So if I wanted to figure out about this person, the best way to do that is really figure out the people around them, right? Maybe if we have mutual friends, talk to them. If I know maybe some of their family that I'm like friends with, maybe I could say, hey, you know, how's such and such, number 3, are they a good person? You know, something like that. And that's like, technically that's what we do. If we want to figure out what's going on at 3, we can just get closer and closer to 3. Now look, there's 2 ways to get closer and closer to 3, from the left and from the right. Because, you know, 3's on a number line, right? So x and g of x. So there's 2 ways to get closer and closer to 3. We can kind of attack it from the left, and we can attack it from the right. So if we go from the left, let's start, you know, numbers to the left of 3, you know, 2, 1, 0. Just for the graph, let's start at 0. And then let's go to 1, then 2. Can't go to 3, but we need to get closer to the left of 3. So let's do like 2.5. Let's do 2.9 and kind of see what we have going on. Now look, I'm going to bust my calculator out. Boom, handy dandy calculator. And I'm going to put this equation into my y equals, right? When I go to y equals, I'm going to put, now look, you got to be careful when you do this. I'm going to put 2 divided by parentheses. Make sure to put this in parentheses. X minus 3. Boom. And now, I mean, I can hit enter, it doesn't matter. I want to go to value. I want to go to calc up here. See that calc button? So second calc value. Now, this is just a graph of it for now. We're going to get to what all that stuff means here in a minute. But notice at the bottom, it lets me put in an X value, and it'll pop out the Y value. So, well, actually, I can go to table for these whole numbers. So I'm going to go to table, actually. So for table, which is over here, I'm going to do second table. And look, it already tells me the answer for 0. Boom. 0 is just negative 0.6 repeating. I'm going to be lazy and use decimals. Don't tell the other math teachers. They don't like that. Okay. And then for 1, I'm going to put in negative 1. For 2, I'm going to put in negative 2. And now notice I can't put in 3. It says error, and it's an error because it winds up being undefined. Okay. So now I'm going to go back to the calc to put in 2.5 and 2.9. So second calc value, I'm going to put in 2.5. Boom. And I know it's kind of hard to see, but it gives me back negative 4 there. Do you see that? Boop, negative 4. And then I'm going to go back to second calc. You can do this by hand if you want, okay? There's nothing wrong with that. But
No,
go to second.
I'm trying to follow you on the calculator, so I know how to actually use this thing a little more. And
I understand.
I got it. I did the same thing, negative 4. Okay.
Wait, so if you put in 2.9, if you see it at the bottom, you get negative 20. Holy cow, that's a big jump. Now let's kind of talk about what we have here. What's happening is we went from 0 to 1. We dipped down a little bit, like 0.4, right? We go to 1 to 2. We dip down to 1. 2 to 2.5, that's only a half unit jump, and we dip down 2. Look, this is only a 0.4 unit jump, and we dip down 16 units. This thing's fallen off. Let's do 2.99. I mean, we are getting really close. Like, this is like asking his or her brother, right? I mean, like, these are kind of like distant relatives or whatever, kind of friends. This is getting real close. We're going to figure out this person. So if I go to second calc value, I'm putting in I know it's glare right there. I'm going to put in 2.99, and I get back, boop, negative 200. Dang, that's a huge jump. So we're going to talk about what this means for a second. So what this means now, the math way of writing this. So I need your brain and your eyeballs here. Look, as x, this means approaches. That arrow means approaches. So as x approaches, what did I say? As x approaches 3. Now, the reason we don't use equals, because we can't equal 3, right? But we're approaching 3. Now, look, we're coming from the left. And if to symbolize coming from the left, you use a minus sign. And you put that right there. That means from the left. Okay? As x approaches 3 from the left, comma, our g of x is approaching. Now look, this thing is dropping off quickly to negative really big numbers. I mean, if you want to put in, like if you do second calc value and you put in 2.999, like his twin or her twin, you get negative 2,000. I mean, this thing is really dropping off. So what we're going to say is that this is headed towards negative infinity. We'll do an example when it doesn't go to an infinity. But so as x approaches 3 from the left, that's what this table symbolizes. As x approaches 3 from the left, g of x is headed to negative infinity. Now on a graph, what does that look like? We'll see. Let's try to get to this graph here. Now we're going to go to positive 3, so let's go to the positive side. We know at 0, we're at 20. I don't know if I can go to 20. I'll try. Let's do it by 5s. 5, 10, 15, 20, right? So negative 5, negative 10, negative 15, negative 20. At 0, we're at negative 0.6. So we're like right there, right? At 1, so if we're going by 5s, I shouldn't go by 5s on this side, but that's okay. At 1, we're at negative 1, so about right there. At 2, we're at negative 2, about right there. But then at 2.5, we're at negative 4. At 2.9, we're at negative 20. Boom. I mean, it dropped off fast. I'll tell you, if you want to look at the graph, it does something like this. So now look, we can't be negative or positive 3. So we're going to put a dashed line, a dashed vertical line at x equals 3. This is called a vertical asymptote. Okay? Vertical asymptote. And we're going to say it's at x equals 3. Okay? So now let's do this from the other side now to show what happens. Okay, so now we're going to approach it from the right. That's going to be a plus sign. Okay, we're going to approach it from the right. And now look, we started at 0. So let's start symmetrically at 0 to 3 would be 3 to what, 6. And then we go 5, 4. And we can't go 3 now, right? So let's do 3.5, 3.1, and 3.01. Okay, so I'm going to go back to the calculator. My equation's already stored in here, right? So I'm going to go to second table, and I'm going to go to positive 6 now. And you'll see some symmetry. Positive 6 is 0.6 repeating. I'm going to just put that on here. 0.6 repeating. So 6 is about right there, 0.6 repeating. And then 5 is positive 1. About right there, right? It's not perfect. Oh, I need to go the other way. 4 is positive 2. So about right there. Now, we can't do 3.5, so I'm going to do the whole second calc thing. And we can probably guess by symmetry it's going to be positive 4. But I'm going to do this just to make sure it's not valid. Okay, second calc value. 3.5. Why is it not valid? Attempted to use a variable or function where it is not valid. Okay. Y equals, did I do something goofy? Nope. Second quit. Second calc. Value. 3.5. What in the world? I have never had this issue before. About 3.1. is going on? I don't want to have to do this by hand. 2.5. It let me do 2.5. It's not letting me do 3. Oh, you know what? Maybe the Zoom standard. Maybe it's because my graph wasn't showing it. I hit Zoom standard. You'll see. Look, do you see how it goes down there? That's what we've graphed right here. So maybe that's the reason. Second calc value 3.5. That was the reason. Okay. 3.5 is positive 4. All I did was I hit Zoom. You go to the Zoom option, which is right there. And if you hit Zoom standard, it'll pop it. It kind of bring it back out. Okay, so then
mine was looking like that. Yay! When you just pulled that up, I was like, yay! That's what mine actually looks like.
Yeah. Oh yeah.
I haven't went as far as you have either. So
I got you. So 3.1 is 20, and then second calc, I bet 3.01 is going to be 200. 200. We're right. So again, what's happening on the other side is we're zooming up this way. Okay, and we know that. The graph shows that. I mean, if you're looking at it. And so what that means, though, in math talk, I'll have to write it. I'll write it up here, guys. I know it's kind of goofy, but look, as x is approaching 3 from the right? Remember, right's the positive. So as x is approaching 3 from the right, the y values, g of x, go to infinity. G of x heads to infinity, okay? And when that happens, when we go to infinity on two sides, and actually all it takes is for us to go to it on one side. But if we go to it on either side, what that means is we have this nice vertical asymptote right there, okay? We'll get into the rules about vertical asymptotes here in a minute, because there's two things that can happen with restrictions on the domain, and I want to get to the other one. Then we'll make some more definitions about vertical asymptotes here in a second. Okay, but visually, that's what they look like. And you'll notice on your calculator when you graph it, it doesn't do a vertical line. Some of them do, but it doesn't do a vertical dashed line if you have one of the newer calculators. Some calculators make like a straight line. It's actually a glitch in the pixels. Okay. So any questions about this other than I think I need to see another example. Let's go over what else can happen actually with a restriction. So I'm going to do, you know what, I'll use the same exact restriction. So let's say we had h of x equals x squared minus 9 over x minus 3. So look, I'm going to get the same restriction. I'll tell you, the first question on all of these should be, what's the domain? And you're going to tell me, hey, x minus 3 can't be 0. X cannot be 3. Now, that's not what we're really going to box in, but that's our restriction, right? What we're going to box in is the interval notation for this. X can be anything. It just can't be 3, okay? So look, something kind of crazy is going to happen when we do the same thing we did before, though. I'm going to go from the left. Actually, I want you to try this one. I'm going to give you a little bit. And I'm going to use the same exact number. So 0, 1, 2, 2.5, 2.9. Okay. I don't think we'll have to do more than that. So let's go. This is from the left. And then the other one's from the right. So we got x, g of x. Now from the right, it would be like 6, 5, 4, 3.5, and 3.01. So I'm going to give you a few minutes to fill this table out. Remember, if you want to put in your calculator to make your life a lot easier, do parentheses x. Now there's a squared button here. Minus 9. Ooh, I don't know why I said that. Minus 9 parentheses divided by x minus 3. So that'll make it a lot easier. Like when you go to the table, you know, you can fill these out. Like 0 is just 3. 1 is just 4. 2 is just 5, and look, we get the error again. And then 4 is 7, 5 is 8, 6 is 9. You have to plug in to get the other ones. But try that. So I want you to fill this out. as x approaches 3 from the left, what is our g of x headed towards now? And then same thing over here. As x approaches 3 from the right, what is our g of x headed towards? And you'll see it's not going to be infinities this time, okay? So check that out. I'm going to get some water real fast. My throat's a little dry. I'll be right back. Okay. Uh-oh, where'd my purple marker go? No. Oh, there it is. Lost it. So I'm going to say or guess, you tell me if I'm right or wrong, is 2.5 5.5? And 2.9 5.9? Right? So if I put in like 2.99, it's going to be 5.99. So look how different this one is. I'm going to bring this other one from before back. On this example, as x got closer and closer to 3, this is called diverging, okay? The y value was diverging. It wasn't converging to a number. This is converging to a number, okay? As we're getting closer and closer to 3, this y value is getting closer and closer to 6. It's never going to get there because we can't plug 3 in, right? It would cause an undefined. Okay, so let's go on the other side. 3.5, I'm going to assume is 6.5. 3.01 is 6.01. And if you put in like 3.001, you're going to get 6.001. And notice, as x is getting closer and closer to 3 from the right, the y value is getting closer and closer to 6. It's not diverging. Look, both of these, they're converging to the same number, okay? Now, when this happens, so when our restriction causes a convergence instead of a divergence. Divergence means vertical asymptote. Convergence means we have a hole, okay? We're going to have a hole going on. So let's actually graph this. So if I want to graph this as 0, we're at 3. Actually, we don't get 2, 6, 9. Okay. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. So at 0, we're at 3. At 1, we're at 4. At 2, we're at 5. Oh, at 3, we're really headed to 6, but we won't get there. So we're going to draw a hole. Okay. And then after 6, we're at 4 now. We're at 7. And at 5, we're at 8. And it goes forever like that. Actually, it looks like a nice straight line. Now that's a hole. I should have made that hole bigger. It looks like it's filled in. It's an unfilled hole. Imagine it's an unfilled hole. Okay? It's a circular hole. I didn't draw it that well. I apologize for that. But notice the domain is still negative infinity to 3 and then 3 to infinity. The same thing with our graph over here. Our domain's negative infinity to 3, and then we jump over that asymptote and we go from 3 to infinity. Okay? So but the difference is this converges. Whenever we get closer to 3 on this example, we're converging to a number. We're converging to 6. So therefore, it created a hole at 3, 6. Kind of neat. Okay? And look, these are the two things, the two outcomes from a restriction on the domain. okay? These are the two outcomes from a restriction on the domain. We could have vertical asymptotes, or we could have holes, okay? And we'll do examples. I'll do more examples of these as we go, because it turns out there's a quicker way to do this than making these tables. I know you can graph it, that's fine, but there's a quicker way to do this because for what we're going to do in the next few parts, it's a little easier if we work this kind of the quicker way. Okay, so let me show you what I'm talking about here. If I've got two different functions, let's say f of x equals x squared minus x minus 6 over x minus 3. I don't know why I'm choosing x minus 3 over and over again. The very first thing I want you to do with this question, always, even if I don't ask you, I want you to find the domain. So x minus 3 can't be 0. Therefore, x can't be 3. And we know, because we've done this 3 times now, I need to get a little more original with these examples. Boom. And now the next part of this, I'm going to ask you, does it have a hole or does it have a vertical asymptote? Look, because it has a restriction here, that restriction at x equals 3 is either a hole or a vertical asymptote. And the way you find that is actually from simplifying this rational function. This numerator can be factored, right? This is simplifying fractions. That numerator can be factored into x minus 3, x plus 3, okay? We went over that in the last test. We went over it in 1.5. And notice, pulling out the red pen, notice our restriction, or where our restriction comes from, cancels with a factor in the numerator. If that happens, we've got a hole. Okay, at x equals 3. So we wind up, now after the simplification, we wind up with x plus 2, right? But this means we've got a hole at x equals 3. So now a hole is a coordinate, okay? It's a coordinate. So you need the x value and you need the y value. So to find the y value of the hole, plug in restriction after simplification. So you do not have to make the table. You're more than welcome to make the table, but you do not have to. Once we simplified, now we can plug in x equals 3 into our equation. So, our equation simplified is f of x equals x plus 2. F of 3 would give me 5, right? 3 plus 2 is 5. So we have a hole at 3, 5. Okay? We have a hole at 3, 5. That's a coordinate. It's not an interval. It's a coordinate. Now, there's no vertical asymptote here. This restriction can only be a hole or a vertical asymptote. It can't be both. Okay? So there's no vertical asymptote for this example. Okay? There's no vertical asymptote for this example. Okay. Questions about this one? I'm going to do a vertical asymptote one next to show you when that happens. So if we have simplification from the numerator and denominator, we've got a hole at that restriction. So let's look at one that doesn't simplify. Okay? Let's look at one that does not simplify. Let's say we've got, let me move this a little bit. G of x equals x squared minus 4 over x plus 7. Okay? Now part A, I'm going to ask you again, what's the domain? And you're going to tell me, well, x plus 7 can't be 0. Therefore, x cannot be negative 7. Now, that's our restriction then, right? X equals negative 7 is our restriction. But we know that negative infinity to negative 7, union, negative 7 to infinity, that's our domain. Now, part B, what I'm going to ask you really is, do we have a hole? Does that create a hole? Or does it create a vertical asymptote? This restriction on our domain has to be one or the other. Okay, again, it can't be both. It has to be a hole, or it has to be a vertical asymptote. So to do that, we have to go back to the original function and simplify. So this numerator can be simplified. It's x plus 2, x minus 2. It can be factored. And on the bottom, we have x plus 7. Now notice there is not an x plus 7 in the numerator. We've only got an x plus 2 and x minus 2. So because we can't simplify this does not simplify, that means that our restriction is a vertical asymptote. Remember, vertical lines are x equals a number. So we write it just like that. And there's just no hole, okay? There's no hole. Now, if I want to do a quick sketch of this one, I should have done this quick sketch of the last one. But if I want to do a quick sketch of this one, I know I've got a vertical asymptote at negative 7. 1, 2, 3, 4, 5, 6, 7. So it's just going to be this nice vertical line right there. I need a few more coordinates to make it look right, or I could just pop it in my calculator. I'm going to be lazy and pop it. Actually, I say lazy. I'm going to use my tools, use my resources. And I'm going to plug it back into this calculator. And I'm going to say, okay, clear this out. Parentheses, x squared minus 4 divided by x plus 7. And then graph it, just to get a nice idea of what this looks like. Oh, that is not what this looks like. Hold on. X squared minus 4, x plus 7. What is going on? Maybe zoom out of this one. Zoom out. Oh, that's kind of crazy. Cool. Okay, so we've got something that goes like this now. Like that. Notice there's still a vertical line there at x equals negative 7. And it like dips down and then it goes this way. Kind of neat. Okay, kind of nifty. But in the end, we do have a vertical asymptote right there. I'm not looking for perfect on the graph. I know you're going to have a graphing calculator, so I'm not worried about how you graph it, but realize that's what this symbolizes. Okay, that's what this symbolizes. So again, back to really what we're talking about. If we have a domain restriction, that domain restriction is either going to cause a hole or a vertical asymptote. If it doesn't simplify, causes a vertical asymptote. If it does simplify, like the previous one, that means it's going to cause a hole. Now, if it causes a hole, it's written as a coordinate. So we have to find the y value. Now, to go back to this one, if I wanted to make a quick sketch, you're going to just sketch the simplified function. That's just a linear function that has a y-intercept of 2 and a slope of 1. Now I've got a hole at 3, 5 right there. So I know I've got this line that goes like this. Okay, that would be the graph of a quick graph of this function. If I was going to do a quick sketch of that function, it's just a linear function with a slope of 1 and a y-intercept of 2. Okay, a slope of 1 with a y-intercept of 2. Okay, so that's the first thing your book goes over. Actually, is the vertical and horizontal, vertical asymptotes and holes. The second thing your book goes over are horizontal asymptotes, which are a little different because horizontal asymptotes do not come from domain restrictions. Okay, it's not like the vertical asymptote. The horizontal does not come from the domain restriction. Horizontal asymptote, really, I guess I can write this down. This is a true statement. Horizontal asymptotes are the end behavior of rational functions, okay? Now, sometimes rational functions don't have horizontal asymptotes, and that's fine, but they are the end behavior of rational functions. And let me show you what I'm talking about. So if I had, let's say, f of x equals, we'll kind of do an easy one here, 2x plus 1 over 4x minus 3. Now, again, horizontal, I'm not worried about that denominator for the horizontal asymptote. The long way to do this, which I'm going to show you to kind of really explain, it really explains why it comes from the end behavior. We're going to shoot x off to infinity. So to get the end behavior of the graph, I mean, think about it. If we had a graph here, and we want to get the end behavior of it, you could just put in really big x values, right? Put in really big values for x, and it'll tell you where the graph's headed, if it's headed down, if it's headed up, or maybe it's leveling off, and that's what we'll see. Horizontal asymptotes occur whenever this end behavior levels off, and we'll see that with this example. Okay, so let's think of some big numbers to plug in. I'm going to plug in like 10, let's say 100, 1,000, and see what happens, okay? And I'm going to go back to my graph or my calculator. I'm going to plug in y equals, I don't know if I can do the value for this one, but let's see, 2x plus 1 divided by 4x minus 3. I hit graph. Yeah, it's like hard to see. It's a really tight graph. Let's say zoom standard. I don't know if it'll let me put big numbers into this one, but we'll try. I mean, there's definitely a vertical asymptote going on, right? But notice how these end values level out. They're not headed up. Remember that last one, it like headed up, and then this one headed down. They're leveling off. So we're trying to figure out where it's leveling off. Kind of looks like 0. It might not be, okay? So let's put in some numbers here. So I don't think we'll do this, but we'll try. Second calc, I'm going to put in a value. Let's put in 10. Well, let me put in 10. Yeah. For 10, it's 0.5675. 0.567, actually 76 if you rounded. Okay. So let me see if it lets me put in 100. Nope. No, and it's because it's not on our graph. So I'm going to just put 100 into the equation. So 2 times 100 plus 1 divided by 4 times 100 minus 100 minus 3. And I get back 0.5063. I round to 4 decimal places, right? So let's put in 1,000. 2 times 1,000 plus 1 parentheses times 4 times 1,000 minus 3. Oh, hey, we get 0.5006. Now notice, this looks like it's going to something. So let's put in like 10,000. An even bigger number. So 2 times 10,000 plus 1 divided by 4 times 10,000. Not plus, but minus 3. Yeah, 0.5000. I got to add another 0 here. It would really be 0.5001, right, if I rounded it. Notice, look, so what this is telling us is as x is headed towards positive infinity, right? 10, 100, 1,000, 10,000. Our f of x here is headed towards 0.5, right? It's headed towards 0.5, kind of neat. So as x is headed to infinity, 10, 100, 1,000, 10,000, our f of x is actually headed towards 0.5. So this is our horizontal asymptote. So we've got a horizontal asymptote here. We'll show it on both ways, both sides. But we've got a horizontal asymptote at 0.5. So I'm going to draw a dotted line here excuse me, yeah, 0.5. So HA, I'll say HA so I don't have to write it over again. Now look, it's a horizontal line, so it's y equals a number. So y equals 0.5. Okay, let's show it on the other side now. So let's say we went that way, right? 10's out here, 100, it goes forever to the right. Let's go to the left now. -10, -100, -1,000, just to show that it's the same thing, okay? So I'm going to do 2 times -10 plus 1 divided by 4 times -10 minus 3. So 0.4419. So 2 times -100 plus 1 divided by 4 times -100 minus 3. Oh yeah, you can see it's going to 1/2 as well. I know. Don't get too crazy over this one. Plus 1 divided by 4 times -1,000. Oh, no, minus 3. 0.4994. Yeah. Again, so now as x is headed towards -infinity, right? X is going to -infinity. Our f of x value is still headed to 0.5. So that's kind of neat. Okay, so we're headed to 0.5 on both sides. So that's the end behavior. Now look, we do have a restriction. And since this doesn't simplify, it's going to cause a vertical asymptote. So I'll just find that down here. Like 4x minus 3 can't be 0. Add the 3, divide the 4, so x equals 3/4. This is going to be our vertical asymptote. You can flip back a few pages or rewind it a little bit and see how I found that one. But we do have a vertical asymptote here at 3/4. Now, I'm going to be a little lazy. I'm going to go back to my graph because I believe, yeah, my graph's still in there. Now, just to be lazy to fill in the graph, I'm going to say, okay, well, what it looks like is happening is we're kind of following this line here. Now, to the left of the asymptote, we're on kind of the other side. Symmetrically, we're kind of on the other side. Something like that. It's not perfect, but our graph does look something like that. So that is our horizontal asymptote. It wound up being 0.5. Kind of neat. Okay, kind of nifty. Now, there's rules with finding horizontal asymptotes, and I'm going to go over those with you. But I wanted to show this always works. If you want to work it this way, every time it works. But I'm going to show you what happened. What happens with everything in mathematics over time is someone finds an easier, more efficient way of doing it. Okay. And what's happened over time is we found a more efficient way of finding these horizontal asymptotes. And it actually comes from the degrees of the numerator and denominator. Now, again, if you don't want to learn this and you're like, I just want to turn you off right now and not listen, that's fine. You can find the horizontal asymptotes this way every time. But let's look at kind of a shortcut way of doing it. And it comes from the degrees of the numerator and denominator. So let's go back. I'm going to make the rule. So f of x equals, now remember how it was like p of x over q of x. That was at the very beginning of the lecture, that all rational functions are p of x over q of x. And it turns out if the degrees of p of x and q of x are equal. If the degrees of p of x and q of x are equal, then, so if then statement, right? If the degrees of p of x and q of x are equal, then we have a horizontal asymptote. I'm just going to say HA because I'm lazy. We have a horizontal asymptote at y equals, actually, I'm going to say y equals the ratio of the leading coefficients. I know what you're thinking. That's a lot of words for math. And you're right. Let's go back. This is the one I just did. Where's the one I just did? Hold on. Why did I do that? Where did I put it? How did I just work something and it just vanished? Okay, there we go. Let's go back to this one because this is an example of that. Notice with this rational function, the degree of the numerator is 1, right? 2x plus 1, the highest x value, or the highest exponent on the highest exponent on the x is 1, and the same for the denominator was 1, okay? So we have an example here of when the degrees are equal, p and x are equal. The degrees of p and x are equal, okay? And when they're equal, so I'm going to just do this here now shorthanded. When they're equal, we have a horizontal asymptote at the ratio of the leading coefficients. So what that means is we have 2 over 4, okay? The leading coefficient for the numerator is 2. The leading coefficient of the denominator is 4. And now simplified, that's 1/2. Hey, that's what we found, right? 1/2, okay? Kind of neat. So it's the very short way of doing all of this work, okay? The very short way of doing all of this work. Kind of neat. And I know what you're asking. You're thinking, well, why in the world does that happen? I know you're an inquisitive mind and you would like to know. And I'm going to kind of go over it briefly, actually, and kind of think of it like money. Let's rewrite this function. F of x equals 2x plus 1 over 4x minus 3. Let's think of the x values as dollars, okay? And look, we're putting in bigger and bigger dollars here, right? So when we put in $10 in this numerator, we'd have 200 plus $1, right? And then we'd have 400 minus $3. Well, if I had $200 in my bank account and I put in $1, it would probably matter, right? I'd notice it maybe. And if I had $400 and I took out 3, I'd probably notice it, you know, $397, right? But now let's put in 100. If I put 100 in here, we'd have 2 times 100. Oh, wait, that was only $20. Yeah, no, I definitely noticed if I had $20 and $1 went in, or $40 and $3 went out. Definitely noticed. If we put in 200, maybe. But if I put in 1,000, if I put in $1,000, I have $2,000 in my bank account. Like if we look at just the degree terms, right? This would be 2,000. This would be 4,000. With that 2,000, if I add or subtract $1, I'm probably not gonna notice that. Yeah, I'll leave with that next time. Sure, I just saw that. Probably not gonna notice it as much if I have $2,000 in my bank account. If I have $4,000 in my bank account, probably not gonna notice when $3 comes out. Well, look, if I put 10 grand in, if I had 20 grand in my account right now, I'm not worried about $1, okay? And if I had 4 grand or 40 grand in my bank account, I'm not going to worry about $3. So what happens is when you put larger and larger x values into this rational function, the degree terms just take over, okay? They take over. I mean, think if this was like $1 million. If I had $2 million in my account, I would not be talking to you right now. If I won the lottery today, you'd all get A's and we'd go home. And I don't care if you tell my boss, whatever. Okay, I don't play the lottery. It's not going to happen. So if I had $4 million in my bank account, yeah, okay, same thing. But I'm not going to worry about $3. I'm not going to worry about $1 if I've got that much money in my account. And that's kind of what happens when you start loading up huge numbers into X. All of the lower degrees don't matter because the highest degree term just takes over, okay? It just takes over and it takes control of that fraction. Okay, so let's go back to the rules. So if the degrees are the same, it's y equals the ratio of the leading coefficient. So that's the first thing that could happen. The second thing that can happen is if, we'll start it this way. If q of x degree is larger than P of X degree. If the Q of X degree is larger than P of X's degree, we have a horizontal asymptote at y equals 0, actually. Okay. If Q of X's degree is larger, if Q of X's degree is larger than P of X's, we have a horizontal asymptote at y equals 0. I got all my paperwork here because I knew I'd want to use it again. Hold on. So let's go back to this example. This was one of like the first ones we did, and we graphed it. Look, if you go up here, g of x 2 over x minus 3, the degree of this numerator is 1. If you don't have an x value in the numerator, the degree is 0. And the reason is you could write this 2 as 2x to the 0. If you remember, anything raised to the 0 power is 1. Okay, so 2x to the 0 is fine. X to the 0 is just 1. It goes away. It leaves you with 2. But notice what matters for us for this example, we have a degree of 1 on bottom and a degree of 0 on top. Larger degrees on bottom. And when we graph this, you can see it had a horizontal asymptote at y equals 0. Okay, it had one at y equals 0. This line is getting closer and closer to 0. It's just never going to get there. Same thing on the other side. Closer and closer to 0. Okay. Kind of neat. We'll do an example where we go through like all of these here in a minute. Okay. So don't worry if you're like, you don't have time to write that down. Trust me, don't worry about it. We'll get there. Now, the third thing that can happen, of course, is what if the numerator is larger? If P of X degree is larger, this is the easy one. No horizontal asymptote. Okay. If the numerator degree is larger, we just have no horizontal asymptote. Okay. We have no horizontal asymptote, and that's okay. Okay. Questions, comments, concerned, other than we just need to see what's going on here. Okay, so let's do an example, and I'm going to incorporate vertical asymptotes and horizontal asymptotes into this. Okay, so I'm going to give you an example, and this one's actually going to have like everything going on. Okay, this one's going to be sweet. Okay, hold on. Actually, it might not have everything. I can get my document camera to situate here. Let's say we've got f of x equals let's say x minus 1 over x squared minus 4x plus 3. Okay, x squared minus 1 over x squared minus 4x plus 3. Oh, that's fine, Sherry. Just make sure to watch the rest of this. We got some important stuff we're about to cover. So I'm going to go back now and talk about what we started with. So part A was the domain. And then from the domain, we're going to have restrictions here. But from this domain, do we have a hole? Do we have a vertical asymptote? Okay. And then we'll go on. So A, B, C, D. We're going to ask, do we have a horizontal asymptote? Question mark. And then we'll probably just graph it out of that. Your book goes over like a lot more steps on how to graph it, but we're going to use our calculator and just kind of graph it from that. So first off, find the domain. Remember, we're not worried about the numerator. We're going to solve this denominator. That whole trinomial can't be 0. This factors into x minus 3, x minus 1, right? Multiplies to give me positive 3, adds to give me negative 4. And we know that x minus 3 can't be 0. X can't be 3. X minus 1 can't be 0. X can't be positive. Oh, don't know where the 3 came from, but positive 1. So we have these two restrictions, right? If I did the actual domain here in the interval notation, it would be negative infinity to 1 union, 1 to 3 union,
Okay,
3 to infinity.
okay, that's the domain even if you can simplify it, because
Yep.
okay,
We don't worry
you
about
find
the
that
numerator. Remember, we act like that numerator it's the elephant in the room. We don't talk about it. Okay.
until after we find the
You're
domain.
exactly right.
Okay, yes. Okay, my bad. Sorry.
No, you're fine. You're fine. It's a good question. It's a great question, actually, because it is going to simplify, right? I mean, look,
I already got to that part. Sorry.
x minus 1, this is x minus 3 over x minus 1, right?
Mm-hmm.
The x minus 1s cancel, and that leaves us with, I should have given myself more room, but it leaves us with 1 over x minus 3. This is, and I'm boxing it in just so we can see it. This is the simplified function, okay?
Do you have a hole?
But, no, we have a hole.
I said we do then. We do.
Oh, okay. Yeah. We have a hole at x equals 1, right?
Yes.
And we've got to find the y value. So remember, we have to plug it into this simplified function. So f of 1 into the simplified function would be 1 over 1 minus 3. So 1 over negative 2. So the y value is negative 1/2. So the whole is at 1 negative 1/2. Okay. That comes from when we canceled out the x minus 1. Now the x equals 3 does not cancel. So because x equals 3 doesn't cancel, we got a vertical asymptote. Right? Here's our two restrictions. This one created a hole because it's canceled out. This one creates a vertical asymptote because it doesn't cancel out. It's there at the end, okay? Okay, so now let's go on to horizontal asymptote. Now look, the numerator degree is 1. The denominator degree is 2. So y equals 0 is the horizontal asymptote because the denominator degree is larger. That was kind of easy, right? A, B, C, D, E. Let's graph it because we've got a lot going on here, okay? We've got to make sure to graph everything. So x equals 3. Let's start there. We've got a vertical asymptote at x equals 3. We've got a hole at 1 negative 1/2. And then we've got a horizontal asymptote at 0. Well, it's going to be kind of hard to see because it's on top of the x-axis. I'll try to graph it there. There's a horizontal asymptote. And then I'm just going to plug it into my calculator. Now you can, excuse me, you can plug in the simplified version so you don't have to type in as much. There we go. So 1 divided by parentheses x minus 3. And then graph it. That's Sharpie on my screen. And you'll see that's what we have going on. Boom. It's getting closer and closer to y equals 0 on the left. And then same thing on the right. It's coming up from infinity and going this way. Okay. Pretty neat stuff. Okay. Pretty neat stuff.
So using this calculator, after I type the equation in, I have to hit enter before I hit graph, correct?
I think you do. I think it does.
Yeah, I think so. I think so too, because the last one I put in looks nothing like yours, and this one does. So
okay. I bet you do. I bet that's right. Okay,
okay.
I'm going to give you another one, and I want you to do this A through E for me. Okay, I'm going to give you another one. I want you to try this A through E for me as well. Okay, so let's look at this one. Let's say we've got h of x, doesn't matter. And I'm going to steal it from the homework, actually. Yeah, let's say we've got 2x squared over x squared minus 9. So I want you to find the domain first. Hole, if we have a hole. Vertical asymptote, if we have vertical asymptotes. And then I'm going to kind of write this under here this time. That way, if we have to go further out, let's do horizontal asymptote if we have one. And then lastly, let's graph it. So I'm going to give you a little bit of time. I want you to try this and see if we can answer all 5 of those. Okay, I'm going to start on this one. Keep working if you're working. It's okay. There's definitely no need in rushing. But let's look at the domain here. X squared minus 9 equals 0, can equal 0. This factor, I need to think of it factored, just in case we can cancel it. Well, this is x plus 3, x minus 3. No. So x can't be 3 and x can't be negative 3. So it would be negative infinity to negative 3, union, negative 3 to 3, union, 3 to infinity. That's kind of a long domain, but that's fine. But
Okay, one thing, I thought we used brackets, like a bracket next to that -3. Am I wrong?
yeah, and the reason, but let me tell you why. So it's because parentheses mean we can't equal it. Because we
Oh,
can't.
okay.
Yeah.
Bracket means that number is actually included. I just had it backwards.
Exactly. Bracket means
Okay.
inclusion. Parentheses means exclusion. That's a great way.
Okay, that's it. Sorry to ask about an old.
Hey, that's a great. You're not the only one thinking that. I promise. You're just the only one asking. Okay. Now notice nothing cancels with the numerator. 2x squared is kind of just by itself. It's definitely not a binomial. So both these are binomials, x minus 3 plus 3. So nothing cancels. We don't have a hole here. So I need a circle with a line through it, just meaning no solution. We don't have holes. But we do have our 2 vertical asymptotes.
And those are x equals 3 and x minus. Yes. Okay, I got that right.
Boom. Now let's talk about the horizontal asymptote here, though. Look, we have the same degrees, 2 and 2, right? So if they're the same, we're going to look at the leading coefficients, 2 and 1. So it's 2 over 1. So it turns out horizontal asymptote is just y equals 2. Okay? Just y equals 2. So I'm going to put down on paper what we know already, and then I'm going to pop it in my calculator. Oh my gosh, this marker is definitely more stout than the other one. The horizontal asymptote at 2 looks like this. Vertical asymptote looks like this. And then I'm going to graph them. So I'm going to use my utility calculator here. Y equals 2x squared divided by x squared minus 9.
Yeah, I got that. And when I hit enter and graph.
Does it look like that?
No, why doesn't it? Okay.
Go back to your y equals. Does it look just like that?
Maybe I was on the wrong one. Let's see.
Okay.
No, it looks like just nothing but a horizontal line on like.
No. I'm talking about the actual equation. Go back to your y equals on your calculator.
I needed the parentheses, I guess.
Yes.
Okay. That would be the problem.
yeah, big time. What it's doing if you don't use that parentheses, it's dividing those x squareds. That's why you're getting that line.
So, okay, gotcha.
Yeah, your calculator is really good with order of operations.
And that's going to be divided by.
Some cool symmetry going on. Note, hey, you know what? This has y-axis symmetry. If I folded this over, it would be the same graph. Kind of neat. Okay. Really neat, actually. Okay.
Yes.
Okay. Guys, I have to go because I got to go pick up a kid who's not feeling well. I just got a text message. But that's fine. The lecture's over. It's 3:10.
Hope he feels better.
I do too. Let me give you the homework, though. And I'm going to tell you, I really kind of expect you to come in with questions on the next lecture because this homework, this homework is not the easiest. So, and even if it takes you a few days and it's 2 lectures from now you're asking, that's fine. But realize if you go to your schedule, you'll see we only cover 3 sections for this next test. Okay, so this is why you need to hit the homework pretty fast. It's gonna snowball on you if you do not. Okay, so for homework, now your book also goes over slant asymptotes. I don't go over that. That's something we decided as a math faculty that we would not. So it starts on page 406, 1 through 43, and just odd. That's fine. Now 57 through 79, it goes over like the 7 steps of graphing on page 399. You can just focus on these 5 and that'll be fine. Okay, find the domain, find the hole if there is one, a vertical asymptote if there is one, horizontal asymptote if there is one, and then you can graph it with a calculator. I want you to focus on these 5 questions, really these 4 questions. Okay. That'll work. Okay, that's it for homework.
That was page 406, you said?
Yes, ma'am. Page 406.
Gotcha.
Great. Okay. It's time.
Thank you.